right, so I changed the talk. So those who came for that talk, I changed it up a little bit. So I'm going to talk about the next generation Intel RealSense technology, and especially I'm going to focus on depth sensors, and I'm going to focus on hardware. We're an Intel company. It's generally tend to be a lot focused on hardware, so that's what I'm going to do. So the first thing, and you may have seen this before, but our mission really is to try to go in and mimic the human perceptual the human perceptual system. And so that goes for everything from the visual cortex all the way to really understanding what's going on in a scene. And one of the things that you obviously know now is that as part of that process, we also acquired Movidius for their VPU vision processing unit. Our main focus, I'm going through this very fast because I want to do some demos. The main focus areas for us are 3D cameras, tracking modules, and middleware. And the 3D cameras is what I'm going to really put most of the emphasis on today, and talk about the latest thing that we're going to come out with this summer. So I'm here selling you guys on what we have. The other aspect is tracking modules. We've been making a lot of progress, and you've heard almost everybody at this talk, here at this conference saying, look, we need some kind of inside-out tracking, some way to cut the cord and so on. And there's tremendous amount of amazing algorithms. Occipital had a fantastic presentation. And so we do the same thing. We've been all of us have been racing to this goal of creating really good inside-out tracking. And that's what our solution is. But the thing that sets us apart is that we're doing it all inside of a single module, and there's no compute going on in the PC or the desktop or whatever it is you're carrying around. Okay, so first, quick show of hands. Who knows about depth sensors? Excellent. That's half, at least. I will do a quick demo, though. And let me just quickly switch to that. So here we go. So what I'm using now is what we internally call the DS5. It's the official name. It's the RealSense 400 series. And the ASIC that we have inside of here, oh, you guys aren't seeing. No complaints there. Okay, let's see if I can project that over. There we go. Nope. All right, let's do it this way. That works. So what you're seeing there on the left-hand side is the color, and on the right-hand side is the depth. And what's really great about this depth sensor is that it's really the ASIC, the processing that goes into that, that's able to see all kinds of things. It can see black things, it can see black carpets, it can see black shoes, shiny shoes, it can see metal. It really is a tremendous improvement from our previous generation, which I was tremendously proud of 2 years ago. But now we have a new child, and our old child isn't as pretty. So just to show you here the point cloud, this is the point cloud, right? So clearly you can grab any image. Let me pause it, and just, you get the full 3D here. All right, so that was really to show you what a point cloud, what a depth sensor is, and what you get a little feel for what our new generation processor is. And let me exit, go back here, and let's see if we can do this again. There we go. Okay. Our technology is not the only way to create a point cloud, of course, or create 3D. There are many ways to understand the world or see the world in 3D. Structured light, which was the PrimeSense technology that was on the Kinect, quite amazing. Of course, big and bulky, very hard to get into an AR or a VR headset, but amazing technology. Time of flight, the Connect One. Microsoft acquired 2 companies there, and they also put some amazing tech into their HoloLens. Then you have longer range technologies like Velodyne, LiDAR, where you take a single beam and you're sending it around, spinning that single beam around, and you're measuring the time it takes for the light to come back. And you know, they're very expensive modules, are 64 beams that you spin around, but the really nice thing about them is that they can see out to 100 meters or so. But it's not very dense. And then we have Intel. We acquired 2 different companies that were, and we were looking at various different technologies. We started off with actually time of flight, but then we moved to this coded light technology, which was the SR300. It was actually integrated into laptops for what we call user-facing applications. And the range was really 1 meter, and if you're maybe a little bit generous, you would say 1.5 meters. But that was the intended use, you know, you being near the laptop. And then we acquired another company where it's based on stereo vision. This is a company called Tisix, based here in the Bay Area. And we made the R200. But the reason we acquired the company was not for the initial ASIC that we made, it was for the 2nd generation. Finally, we're at a point where we can show that. But it was great, the tech that we had at the time, but it's even better now. So let's just take a walk back 2 years and say what happened when we first got the LR, what we now call the LR200, but the ASIC itself is called the DS4. Well, when you have a hammer, everything looks like a nail. And so one of the things we did was, I did, you know, I started going around and scanning everything. So here's one of my colleagues. Here's my son frozen in carbonite. My daughter sleeping on a couch after a hard day at school. And then we decided, hey, let's bring it down to the Intel cafeteria. And it happened to be bring your kids to work day. And we started scanning kids. And the #1 question we had is, do we do birthday parties? So it was great fun, but we also found that the PC usage was really not resonating, and you'll see that we changed emphasis. But before I do that, you know, doing these types of scans actually helped us. You always have to constantly fight for your funding and your direction and so on inside of a company. And one of the things we did was, one of the first things we did was we actually scanned our CEO. And then we made him out of gold. And that secured the funding. And what happened then was that every CEO that would come in and visit us, we would have to scan them too. And then we had to 3D print them. So it was good fun. And of course, you know, we like to have a little bit of fun, so we didn't just, so we asked our CEO, when we scanned him, he stood like this. Then we said, okay, let's have a little bit of fun. Let's see here, what happened, do you see it? So he's only been scanned from, you know, by walking around him once, but then we could rig him, and we could control all actions. And then the next thing we did was we said, okay, let's scan some of the VPs or senior VPs. And so then we created like this combat game where you could fight. So you know, you only have the fun you make yourself here. So I'm just going to let you see that one. He'll probably say that he can do that. Okay, so what's so special about our next generation? Well, first of all, you know, it's at Intel, of course, but the amazing thing here is in 2 years, we've increased the compute power by 20x. And why do I make such a big point of that? Is because that's where the IP is. It's not, you know, what are the eyes? Because this is a very simple system when you really look at it. It's 2 eyes, and then there's a brain. And the 2 eyes have to look at the world and deduce distance from it, deduce volume from it. And that's what we humans do, and all animals do with two eyes. And you have small animals from mice to big animals, elephants, and they all have different eyes, but the same concept of having this amazing compute to be able to understand the world in 3D. And the other thing that's great about this technology is the thing in green there, which is that it works fully passive. So unlike all those other systems we saw, they all rely on sending out light and then looking at that light, either looking at what time it takes for the light to come back or looking at how the structure changed. And as such, they compete with ambient light, compete with other imaging or other systems that might be also projecting their beams at the same time. But we, of course, know that we humans, we don't have eyes, don't have laser beams shooting out of our eyes unless we're Superman. As such, it's one of the great things about having something that can work passive is that you can have extremely long range, because you don't really have to send that power out with a lot of energy and wait for it to come back. The other thing we did was we increased the resolution to 1280 by 720. At 30 frames per second, and we can also go up to 90 frames per second at lower resolutions. So here's just a quick picture of what it looks like outdoors. This is outside in the Intel R&B building right down the road. And what I like in this image is that if you look at the left, it's hard to see. It's a cluttered scene. But if you look on the right, you can see, let me see here, you can see that there's a tree back there. There's a wall here. The depth actually really helps simplify the computer vision tasks that you want to do. All right, so let's change gears and talk about the markets that we are now interested in. And this is really what the topic of the original talk was to talk about all these different markets. But of course, I'm going to focus on VR MR and why depth sensors are important for this market. But these are all the places that we really think that we can apply our technology. And what we've done is we've spent a lot of time creating these new chips and trying to really bring the price points down, get them down to a level where they can be embedded into all kinds of different systems. So they can be embedded into vacuum cleaners and drones and tablets that are doing shipping logistics, or even cell phones. And I'll talk a little bit more about that in a second. But today I'm going to focus on VR and MR. So you may have seen this before. Achin, our GM, showed the same animation. It's so pretty, I stole it. And the key thing about Project Alloy is we wanted to create a reference platform that we could develop on ourselves and learn from and see all the things that we could then provide as ingredients. Either we provide the whole thing as an ingredient, but we can also provide each of the different elements as ingredients into VR systems. So we will happily work with Qualcomm systems or other systems with the different ingredients that we have. And some of the key ones here is the inside-out tracking, the 6-off tracking, hand tracking and interactions, merged reality, and a few more that I'll talk about. The first one is the ability to move around freely. And we've heard how everybody, and on the panel right before, it would be amazing if you could just walk around and go anywhere you wanted to go. And the way that works for those who aren't computer vision scientists out there is basically where you look at the world and you try to understand your location in 3D space using your inner ear and your eyes. And by combining those two, what you have to do to convert that to that kind of concept that that people used to navigate by with the stars, you convert that concept to a robot, is that basically it looks at a complex scene and only picks a few points. And those few points it tries to localize in 3D space and track them. And then it ends up looking like that. You just have all these points, and each of these points has a unique identity, and you track them in 3D space. But then more importantly, you track your location relative to those 3D points. and that's the inside-out tracking. And what we did was we created this completely self-contained device using the Movidius chip that is able to basically just spit out 6 DOF and not require any compute on the main platform. And what I should say is that's also something that we're bringing to market here this summer. The next thing that depth sensors are good for is the natural interaction. And I think we showed this video as well, but for those who haven't seen it, I will run it because it's so pretty. So here are my hands in VR. And what's great is really this ability to look down and merge realities, merge the real world with the virtual world simply by looking down and capturing your hands in 3D and instantaneously extracting them out of the real world and putting them in VR. And the nice thing there is we can take any object, tools or anything and use them in our VR world or AR world even. Of course, what would be nice is, can I leave those objects in the VR world? Could I just pick up something, look at it, put it down, and then it actually stays in the VR world, and then I could possibly share it. So those are some of the things that we're looking at, and I'll show you just in a second. The other thing, though, that's good for VR is controllers. Yes, we love hands. It'd be nice if 80% of what you did was hands, but we also know that many things we need to have controllers. Whether you want to call it a sword or a stylus or a gun, there's just a need for controllers. And ideally 2 controllers. So everybody should be able to have 2 controllers that are also tracked in 6 degrees of freedom. And they have to be tracked exactly relative to your headset. So these are big challenges, and that's what we're working on. The other thing is we want to democratize the creation of worlds. You should be able to put on your helmet and just look around and scan in the world. And instantaneously, somebody else should be able to put on their helmet from across the world and walk around in the world that you've just created. And so that's using the SLAM and 3D reconstruction in order to create high-resolution 3D content. And you shouldn't have to sit by a computer and map out and draw for hours. How am I doing on time? Draw for hours in order to try to create a 3D world. Although, of course, you can do that too. The other thing I should say that we have with our 3D sensor is collision avoidance. So we can very easily map out this world so that once you put on your helmet and you have your inside-out tracker and you don't have any cords hanging off you, you will start walking around. And as soon as you start walking around, like we heard in the panel earlier, you're going to bump into stuff. And we don't want that. So we want to be able to have some kind of sentry or some kind of blending of the real world in when you are about to hit it. And that's a very key aspect of depth sensors as well. As soon as you get close to something, it merges into your, fades into your virtual world. So what about content? So, this concept of being able to look at something and then leaving it in the 3D world or the virtual world. So here's something we actually scanned with our previous generation, the R200. And what's great is just the quality is amazing. And this is the type of stuff that now can start open the floodgates for sites like eBay or something like that, where you can post content that you've created by simply looking at it, or maybe having scanners where you scan them, hand scanners. It'll be important to do things like, hey, I wanted to buy a bike on eBay, and then it finally arrives, and it turns out it's a little toy bike, or it's it's too small for you. If you can just grab that, look at it in VR, walk around the bike, and say, yeah, that's the size that I need. Things like that are important. The world is 3D. We've been experiencing it in 2D. It's time to really experience and merge the 2D and the 3D world. Of course, no computer vision stuff is complete without lots of pictures of yourself. So here is mine. Now, what's nice about this is that this was captured with a very quick, it was with a device that's this big, And basically, you can imagine the type of form factors this is for. This type of stuff. And this was basically just me holding it out like that and grabbing myself, my photo of myself, and not doing, not grabbing myself like that. But none of this scanning around, doing all kinds of stuff. It was basically just like that. So we have different form factors, but we also have some experimental big ones. And so here's a slightly bigger one. This one we are also sampling to customers. If you want to, I'll show you how to get a hold of it later. But basically, it's how do you get longer range with stereo? Well, the wonderful thing is that same ASIC can be used with very little changes. So what we do is we build different modules. And in this case, in order to get longer range, you increase the baseline, so the distance between the eyes. And you can also narrow the field of view a bit. So basically telephoto lens type of stuff. And then you can see things farther. So a few weeks ago, I went down to Avaya Stadium, and I was able to bring my depth camera. They allowed me to bring it in. Went through security. And so here's a scene, and I was going to show it to you in 3D. So it's 50 meters to the goalie. And this isn't post-processed or anything like that. This is just the raw data per frame. You can kind of see where the ball is at any time. All right. And then one last thing, one of my last things here is there's also a very important element of VR, which is the social element. You'd like to be able to go in, this can allow you to teleport people, right? And there's amazing software development being done by all kinds of groups to try to merge multiple point clouds together to create a full 3D dynamic fusion point cloud or surfaces. But there's also the aspect of once you're in VR, you want to have a social element to it. And one of the most important things about social aspects is the face, the face expression, and so on. So I believe there's also somebody here at the conference that basically has a little headset that has a small sensor where it looks, a depth sensor looks at you. And you can take this same little thing here and basically capture all those expressions and instantly teleport yourself into 3D with that. So in this case, this is mounted underneath a helmet. Okay, so these are a few of our SKUs. I'm not going to go into a big detail here about it. It gets more expensive from the bottom to the top. The sensors change a little bit from rolling shutter to global. From rolling shutter to global shutter. The angle, the field of view gets a little bit bigger, and so on. But there's a lot of flexibility, and here's what a set of them look like. This is the what we call the RS410 and the RS430. And then finally, just a teaser here for something. Again, I just want to say this one's not one we're selling right now, but you can imagine the types of form factors we're going after. Here's our little, very versatile, small depth sensor. All right, so resources. This is look at these for some links to how you can get a hold of some of the things we have. And I've put our marketing guy up there, Anit Chopra. Please contact him with any questions. And only in an emergency, contact me. All right, thank you.
So we have time for some questions now.
Oh, thank you.
Looks like we had one come in through Slido.
Yeah, that's great. So power consumption. Whoever did ask that. Nobody? Okay. That's a really good question. So the great thing about this one, so the ASIC consumes 600 milliwatts of power when it runs at the highest resolution, highest frame rate. And as you go to lower resolutions, lower frame rates, it scales down very gracefully. And just to put that in perspective, this IP that's inside of this ASIC, of course you can run this on a PC, on a GPU or CPU, whatever. So we have a C model. Before we make an ASIC, we have a C model. We run it, and we're constantly doing development on these algorithms. And currently, we have an extremely good algorithm, but it takes 3 minutes to calculate a single frame on 4 cores of an i7. So that's basically what you're getting for 600 milliwatts inside of this small device.
Would anyone like to ask any questions directly? We've got a couple minutes. All right. Well, thank you very much. Oh. All right.
Oh, over there. What about in-headset expressions? Yeah, good question. So there are some companies that are looking at putting cameras inside, and I think that's a good idea. There's also companies looking at putting sensors around the headset to kind of try to deduce the expressions as well. It's also kind of interesting. I do think the eyes are definitely very important for that social element, so I do think we need to figure out something to do there. It's not something that I'm working on. Oh, we do large-scale public space AR installations. Can we play with the wide space sensor? Yes. All right.
Okay, let's hear it for Anders.